Hello, I'm Omid. I'm a master's student at the University of Calgary and I work with Dr. Safavi-Naini. And today I'm gonna present our accepted short paper to the FC conference. So first, today I review the definition of verifiable random functions, then XMSS signatures, which are post-quantum hash-based signatures, and then I explain X-VRF construction, which is based on XMSS, and it's a post-quantum verifiable random function. And then I present our main contribution in our paper, which we showed the flaw in security of X-VRF, and we propose an efficient algorithm to break the uniqueness of X-VRF. And then I will discuss consequences and future works. So verifiable random functions, or VRFs, first proposed by Mikhaili, Rabin, and Vatan. And we can see VRFs as a public key version of pseudo-random functions. So each user has a public and secret key. Public key is public and secret key is private and needs to be kept secret. And then for any input x, the key owner first calculates the output of the function, which is pseudo-random. This is an important property of verifiable random functions. And also, each user provides verifiers with a proof, P, which cryptographically proves that the output is calculated correctly. And this is the nice property of verifiable random functions, and VRFs have wide applications in proof-of-stake-based blockchains like Algorand, key transparency protocols, and zero-knowledge proofs. So in this slide, I'm going to review the construction and main properties of verifiable random functions. So first, we have key generation algorithm, which input is security parameter, and the outputs are secret and public key. And then in evaluation, the inputs are an input that we want to calculate the output for that, and secret key. So without secret key, nobody can calculate the output. So you need to have the secret key to be able to calculate the output and the proof. So for any input x and secret key, one can calculate output and proof. And then in verification, using input, output v, proof, and public key, one can verify and see whether the output is calculated correctly or not for a given public key. And we need to have three main properties in any VRF scheme. The first one is verifiability. If the evaluation algorithm is honest, correct, so verification should accept the output for that input with probability 1. And then we have two other main important properties. The first one is uniqueness, which means that for any input, we only have one output, because verifiable random functions are functions, so each input must have only one output, and this should be whole even if the key generation is not honest, and even if public key is malicious. So for any public key, even if it is malicious, just it needs to satisfy the verifiability property, but it may not be necessarily the output of key generation. It can be constructed in any way. So for any public key, we must have this uniqueness property. And finally, we have pseudo-randomness property, which means that the output v in evaluation algorithm must look to a random output of the same length, and nobody can distinguish this string from a completely random string. And there are some non-post-quantum VRF schemes based on hardness of factoring. That is the first paper that introduced verifiable random functions, and later some proposals based on discrete logarithm and elliptic curves developed. These schemes are vulnerable to quantum attacks, and adversary can potentially derive secret keys from public keys, so we don't have that behavior, and everybody can calculate the output, so there is no security here. And also we may not have pseudo-randomness anymore, and people can distinguish the output from truly random output. So there are some post-quantum VRF schemes that are developed based on hash-based signatures, lattices, and isogenies, which are type of problems that are believed to be secure against quantum computers. And X-VRF, which is our main topic and VRF that we talk and our contribution is about, is a hash-based signature scheme. So to explain X-VRF, first I need to explain hash-based signatures, and then I will explain X-VRF. So hash-based signatures are based on hash functions. So in this slide, I just review the main properties of hash functions. So a hash function family is a family of functions, a group of functions that maps strings of arbitrary lengths to strings of length n, and each function has a key. So this hash function family is parameterized by a key. And we have three main properties. The first one is preimage resistance. So preimage resistance means that for any random key, this is important, for any random key and output of a random input, it's inefficient to compute the preimage, the actual input. So for any random function, if I choose a random function from the whole members of this family, and I select a random input and calculate the output and give that output to the adversary, adversary cannot compute the input from the output. So this also means one-wayness, or we say preimage resistance. The next one is second preimage resistance. Again, for any random function and random input, it's inefficient to compute another input such that these two inputs are distinct but the outputs are the same. And finally, we have collision resistance, which is for any random function. It's inefficient to compute two distinct inputs with the same output. So the difference between second preimage resistance and collision resistance is that in second preimage resistance, we have one random input, and then we want to compute another random input, another input for that. But in collision resistance, we don't need any randomness, and those two x and x prime can be any value. And then we have hash-based signatures, which are signature schemes that security is based on securities of hash functions and are secure as long as the underlying hash function family is secure. And XMSS is standardized by NIST as a post-quantum stateful hash-based signatures. And to explain XMSS, I need to explain two terms. We have one-time signature schemes, or OTS, which means that the security is guaranteed for signing only one message for each key pair. So if I use one key pair, public key and secret key, for signing more than one message, there is no security guarantee, and maybe adversary can easily forge the signature. So for each key pair, I can sign only one message. And also we have many time signature scheme concept, which is a signature scheme that the security is guaranteed for signing up to n messages, and n is usually a reasonable large number, like 2 to 30, 2 to 50, and that range depends on the scheme. And XMSS is a many time signature scheme, which I explain in the next slide. So XMSS, as I explained, is a many-time signature scheme. So at the bottom level, or level 0, you can see J0, layer 0. So we have a votes plus scheme, votes plus signature scheme. Votes plus is a one-time signature scheme, which I explained in the previous slide. So votes plus is a one-time signature scheme, and in layer 0, or the bottom layer, we have 2 to n votes plus key pairs. Each of these key pairs can be used to sign one message. And then we use a construction, a binary tree, which is known as Merkle tree, to construct this tree. So we hash votes pk0 and votes pk1, public keys of votes signature scheme, to obtain the first node in layer 1, one layer on top of J0, layer 0. Then we hash votes plus pk2 and votes plus pk3 to obtain another node, and we continue this one. So now we are in layer 1, J1. Then we continue this process to obtain one node on upper layer, and we continue this process until we have only one node, and that's the root of the tree. And the root of the tree is our public key. So this is our tree. So each time we want to sign a message, we use one of these votes plus key pairs. As I said, each votes plus key pair can be used to sign only one message. So each time, for the first time, I use votes plus pk0 sk0 to sign my first message. For the second message, I use the next one, and so on. We continue this process. So the signature of XMSS is signature of the used votes plus signature, plus the index of that, and plus authentication pass. So if I don't have this authentication pass, I need to publish the whole tree so that verifier can verify that this public key is included in the tree. I need to publish all the nodes, intermediate and bottom and the root and so on. But a clever way is to, instead of this way, we can publish just an authentication pass, which allows the verifier to recalculate the root without knowing all other nodes. So suppose that I am signing the first message. So I use votes plus PK3 and SK3, and I sign that message. And now I have votes plus signature, part of the XMSS signature, index, which is 3. And then authentication pass is the value of all these gray nodes that are grayed. And you can see one of them is votes plus PK3, the value of this node, and one value in top upper layer and one in the upper layer. So verifier doesn't need to know other nodes. Verifier can easily use these nodes to recalculate the root. And in this case, instead of publishing 2 to n nodes, I just publish logarithm of 2 to n, which is n nodes. And it is way more efficient than publishing all the nodes. So this is XMSS signature. And for signing the next message, I use the next votes plus key pair. Also, we have some randomization elements and some detailed technical parts, which I removed and are not related for this topic. And this picture is taken from this reference, this paper. And then we have X-VRF construction. X-VRF is first post-quantum VRF scheme based on symmetric primitives. It's practical, and authors claim that it can be used in Algorand blockchain readily. And X-VRF is constructed on top of XMSS signature scheme and uses a state from Algorand to fix a problem, which I will explain. And authors propose a relaxation on the uniqueness. So first, let's review the construction. So a construction of X-VRF is that the main idea is to use the XMSS signature scheme and assume that we have a random oracle model, and then just give the signature of the input to that random oracle, and output is VRF output, and the proof is signature. So receiver can first verify that signature is calculated correctly for the given input, and then check and see that the output is hash of that signature. And because we are in random oracle, we know that the output has pseudo randomness property. The problem is that, as I said, we have many votes plus key pairs. So in XMSS, for signing one message, we can use this one, or for example, votes plus PK0, votes plus PK1, and so on. And for one message, we might have many signatures, and different signatures result in different hash outputs and VRF outputs. So for one message, we have more than one VRF output. And this is the problem, that we cannot readily just use XMSS and apply a hash function to obtain X-VRF. And authors of X-VRF had a novel idea that they used a state from blockchain, Algorand blockchain, to fix this issue. So in fact, this index is forced to be some fixed value that is defined in blockchain, Algorand blockchain, and nobody can deviate from this procedure. And if I use if index, for example, is 5, and if I use index 6, verifiers can check this and reject my output, and they can easily check this procedure. So this is the claim. This theorem is taken from X-VRF, and if we use the same counter or leaf index, we have computational uniqueness and pseudo-randomness. So these are the algorithms of X-VRF. Key generation is mainly just XMSS key generation. We obtain public key and secret key. As I said, X-VRF is constructed based on XMSS. And in evaluation, we have input, and also we have secret key of this votes plus signature scheme, or our XMSS signature scheme. And also we have an index from Algorand blockchain. So this index forces us to, for example, use node with index 3, 2, or any other value. So we have the secret key of votes plus, and we calculate the signature of that input, and nobody else can do that because nobody knows this secret key. And we easily use this secret key and index and input to calculate the signature. And we also calculate the hash of the signature, and the proof is signature and output is hash of the signature, and output has pseudo-randomness property. And because we are not allowed to use other indices, we are sure that we have, they claim that we have uniqueness property as well. So in verification, verifier receives public key, input, output, and proof. And verifier first verify the signature using public key and input and proof, and then verify the output and check to see if the output is hash of the signature or proof or not. And if everything is fine, then verifier outputs accept, otherwise outputs reject. And again, we use this Algorand number or index or state from Algorand blockchain. So our main contribution was that we showed that even if we use the same index for any message and for any secret key, we can output more than one value for any message. So even if the function family is a collision resistant hash function family or second preimage resistant hash function family, again, for any secret key and any message, we have more than one verifiable output. So we first showed this for votes plus signature scheme. We showed that we can design our public key in a malicious way such that we still have verifiability property, but using that public key, we can have two verifiable votes plus signature schemes for a message. Then we use that votes plus malicious key generation, and if we have two distinct votes plus output signatures, we have obviously two distinct XMSS signatures. And if we have two distinct XMSS signature schemes, we have two, with a high probability, two distinct X-VRF outputs. And in this way, we showed that for one input, we might have more than one output, two outputs or any other. And this is the main lemma in our paper. We proved this lemma, and also we proposed efficient algorithms that for any message and any secret key, we can calculate more than one verifiable output. And then we proposed this algorithm, and finally we showed the flaw in security of proof, because X-VRF had a provable security of uniqueness. So we proposed an attack and showed that X-VRF doesn't satisfy uniqueness. And also the flaw in the security proof of X-VRF is this red line that I am showing here in this slide. And this lemma is taken from X-VRF paper, and authors claim that if the hash function is collision resistant, then this XMSS signatures are same. And we showed that this is incorrect. And also we proposed an efficient algorithm to propose two distinct signatures for one message. So the thing is that VRF uniqueness implies that for any public key, even chosen in malicious way, as I said, it just needs to satisfy the verifiability. We shouldn't be able to have two outputs for that input. And as I said, our contribution was to show that we can deviate from actual key generation algorithm and have malicious public key and secret key generation, such that for one message we can have more than one verifiable output. And so what is the problem in the security of X-VRF? So this line, if the hash function used in XMSS definition is collision resistant, we might have two different interpretations from this line. The first one, if maybe authors suggest a single collision resistant hash function. This is one thing that pops into mind at first glance. So maybe they meant just a single hash function family, but technically this is not correct. And I have these quotes from a paper by Ragway and Shrimpton from 2004. And in a collision, we definitely have a polynomial time efficient algorithm that can output collisions for that any hash function, single hash function. The thing is that we might not know that, but definitely that exists. So technically there is no single hash function, collision resistant single hash function. And you can see in these quotes that trivial adversary would prevail if the key were fixed, and it makes no sense to have both the key and challenge is the input, both the key and challenge being fixed. And because in collision resistance property, challenge is not random, unlike second preimage resistance, so key should be selected randomly, and it cannot be any arbitrary member of the function. And also, X-VRF is constructed exactly based on XMSS, and in XMSS we have a hash function family, and key is selected randomly in key generation procedure. So it completely makes sense to follow the similar procedure and use that for X-VRF, because in X-VRF authors explain that X-VRF is based on XMSS, and I showed you the construction and the key generation, and the keys, public and secret keys, are exactly XMSS keys. So, and in XMSS we have a hash function family and we select a random member. So here it completely makes sense to have a group hash function family instead of a single member, a single function, because of these two reasons. So now suppose that we have hash function family, collision resistant hash function family, and the thing is that definition of collision resistance just as guaranteed collision resistance for a random member. So this is the formal definition of collision resistance. For any random key, it's inefficient to compute two collisions. But if we choose a member non-randomly, arbitrary, there might be some collisions, and it's not against the definition of collision resistance. And in fact, we used this idea, and we proved in our paper in this main lemma that even if the function family is collision resistance, if there exists only a single known function member of this family, which we know a collision for that, even if it's collision resistance, we can use that to calculate two distinct outputs for any given secret key and any message. And finally, I want to discuss the consequences. So if, as I explained, X-VRF was developed for Algorand blockchain. In our paper, we showed that it doesn't satisfy uniqueness, and if key generation is not trusted, and adversary, instead of using a random key process and function selection from the function family, uses a malicious procedure. So in that case, X-VRF cannot satisfy uniqueness property. And this means a malicious user can generate more than one output for a given input. And our algorithm works for any secret key and any message. So we break the uniqueness and we violate the uniqueness of X-VRF. So X-VRF doesn't have uniqueness, even if we use the same counter. So if we have this, there are some implications in real world in Algorand, because X-VRF is developed for Algorand, and in Algorand users are not trusted. It's a permissionless blockchain, and anybody can join the blockchain and participate in the block generation. So, and there is no control on key generation of the users. So malicious users can calculate more than one output. And in this way, based on the construction of Algorand consensus algorithm, users can increase their chance, double their chance of being part of the committee for next block proposition. And because of that, malicious users can increase their chance without increasing their stakes in the network. And this might cause some problems in the network of Algorand network. But the only thing is that our proposed attack doesn't readily find two collisions calculate more than one output for a given input. And the reason is that X-VRF implementation is based on SHA-256 function, which currently there is no known collision attack against SHA-256. And because of that, we cannot propose more than one output for one message at the moment. But what we showed was that X-VRF doesn't satisfy formal and provable security, even if we have function family. But in real world, because we use SHA-256, at the moment there is no known collision for SHA-256, and we cannot readily calculate two outputs for a given input. And finally, for future works, we are going to conduct an in-depth analysis of the attack that we propose on Algorand network. So our attack double the chance of adversary to propose to be part of the next committee, but it needs a more analysis to see the effect of this on Algorand blockchain. Also, one interesting line of research is to check other existing hash-based signatures, one-time and many-time signatures, to see if they have the similar problem or not, and can we construct a secure VRF based on hash-based signatures with some small modifications on those schemes or not. And one other very interesting idea is to construct a hash-based signatures, maybe with completely different idea, and then assume we are in random oracle model and we can obtaining a verifiable random function by applying that random oracle or hash function to the output of the signature. But we need to satisfy uniqueness at the first step. Thanks for your attention.